So first off, I just want to say thank you again to the CIM for giving me this opportunity to share some of my work here with everybody. And I hope that everybody enjoys the presentation and their time here. So today we're just, as Pete mentioned, we're going to be talking about how we can apply mineralogy and mineral chemistry as a way to develop mineral deposit models and exploration tools for conduit type nickel copper PGE systems with an emphasis on the eastern gabbro of the Coldwell complex, which is located approximately 4 hours east of Thunder Bay. Now, there's obviously been a lot of work done like this on different deposit types, including nickel copper PGE systems. So we're really going to be focusing on, trying to highlight the challenges in developing these models for these systems as a result of this complex interaction between magmatic and hydrothermal processes. So we can split this talk up in two main themes. The first theme is going to look at how we can develop genetic models for these systems, and the other aspect is looking at how we can develop exploration tools to kind of vector towards the mineralization. So in terms of the genetic aspect, we're going to be looking at iron titanium oxide and sulfide mineralogy and texture and chemistry as a way to characterize the evolution of the eastern gabbro, as well as the different processes that generated and modified the mineralization. And the exploration aspect, we're going to be characterizing or identifying geochemical signatures in both iron titanium oxides and vein-hosted silicates that we can use as a way to vector and identify mineralization. So as I just mentioned, we're going to be focusing our attention on the Coldwell complex, which is an alkaline complex located on the northeast shore of Lake Superior, and was placed into the North American mid-continent rift approximately 1.1 billion years ago. Now we're going to be zooming in a little bit further here onto the eastern gabbro, which we can see here in this light pink color. It wraps around the eastern and northern margins of the complex and comprises of a variety of mafic and ultramafic rocks. Now there's four main zones of mineralization in the eastern gabbro: the Marathon deposit, Fort Dams, Sally, and Redstone. Now we've arbitrarily grouped these into kind of two groupings. The first is simply comprises the Marathon deposit, and the other grouping we term the northern deposits, and that's basically every mineralized zone that occurs north of Marathon. So the eastern gabbro itself can be comprises three main rock series, and from oldest to youngest, these are the metabasalt, the layered series, and the Marathon series. Now, at the time that this study was being done, the genetic model suggested that each of these gabbroic series was genetically distinct, meaning that they crystallized from melts that originated from different magma sources. Now, one of the problems with this is that a lot of this interpretation was done using whole rock chemistry, and this was problematic in the sense that many of these rocks represent cumulates, and so whole rock chemistry may not accurately reflect the composition of the melts from which they crystallized. So there was still some debate regarding the genetic relationship between these three rock series and the role that magma mixing played in their development. Something that I forgot to mention here is that of these three rock series, only the Marathon series hosts copper and PGE mineralization, and so it's the most economically important within the eastern gabbro. Most of the work that has been done on the mineralization in the eastern gabbro focused on the Marathon deposit. Now, mineralization here and elsewhere throughout the eastern gabbro is largely restricted to the Tuduck Lake gabbro, which is a coarse to pegmatitic gabbro that exhibits a subophytic texture with cumulus, plagioclase, and interstitial pyroxene and magnetite. Now, at Marathon, mineralization is largely restricted or occurs largely in three dipping zones: the footwall zone, the main zone, and the W horizon. Now, each of these zones is mineralogically distinct, and we're going to get into this later on in the talk. And they are characterized by distinct copper-platinum ratios, with the footwall zone having the highest ratios and the W horizon having the lowest ratios. Now, although all of these zones are hosted within the Tudic Lake gabbro, their relationship to one another was never really characterized, nor were the processes that generated and modified the mineralization. So that's
Matt, you seem to have frozen.
Maybe not enough bandwidth.
Yes. Lost him completely.
You may have to go out and come back in.
Which I think is what he's just done. All right. Sorry about this.
Joys of digital.
We will have him back soon, hopefully.
There he is.
Matt, welcome
I
back.
am sorry. I've been having internet problems since last night. My nightmare came true. Could you give me access for screen sharing?
Yeah,
Thanks.
you should be good.
So where did we leave off?
You were, yeah, you were just talking through this slide still.
Right. So I'm sorry if my internet cuts out again. I'm not sure what's going on with my internet today. Right. So after the Eastern Gabbro formed and the mineralization, the whole system was fluxed by hydrous fluids, and we know this because there's a complex set of veinlets that cut across all of the rock types. And so the question is whether or not these fluids mobilize the metals upwards, and if this is recorded in the chemistry of the veins, and if this can be used as a way to vector towards the underlying mineralization. All right. So the first thing that we're going to be talking about here is the application of iron titanium oxides
We've lost him again.
Yes, we have. This is not going well. Yeah, it looks like he's completely stuck. All right, well, we'll let him regroup and we'll try one more time. And if it doesn't work a third time, we'll maybe postpone the whole talk for another day when we can get him some better internet. He's back again. Hey, Matt.
I'm sorry. This is a disaster here. All right. So continuing on.
So back, Matt. We were still looking at your two model slide with that one when you dropped out.
Okay, perfect. So right. So we're going to be focusing first on the application of iron titanium oxide, mineralogy, texture, and chemistry as a way to understand the magmatic and post-magmatic evolution of the Eastern Gabbro. So iron titanium oxides throughout the Eastern Gabbro exhibit a range of exsolution textures. So here we have a typical cloth textured iron titanium oxide that at this scale in reflected light appears relatively homogeneous. But if we zoom in a little bit into this area, we can see actually that they contain this complex network of oval spinel and magnetite. Now, on the other textural extreme, we have these trellis textured iron titanium oxides which you can see here contain these coarse lamella of ilmenite in a matrix of magnetite. But zooming in a little bit again, you can see that's a little bit more complex than that. And they also contain these finer lamella of trellis ilmenite, as well as these blades and amorphous, I guess, blobs of spinel. Now we can also get a range of intermediate textured iron titanium oxides, which are coincidentally termed intermediate textured intergrowths. And they can contain these coarse ilmenite lamella and these spinel in black here, but otherwise appear relatively homogeneous. But just as we always do, zooming in, we can see that in all sense of the word, they are in fact intermediate in the sense that they contain both trellis ilmenite as well as this cloth textured oval spinel intermediate to the ilmenite. So the question is then, how do we get these different textural varieties of iron titanium oxides? And does this process affect the trace element content of the intergrowths? So here we have a ternary diagram showing the relative proportions of iron 2+, iron 3+, and titanium 4+, with the known solid solutions between magnetite and oval spinel and ilmenite and hematite. Now, as you can notice from this, there's actually no solid solution between magnetite and ilmenite, yet intergrowths between these two phases is much more common than magnetite oval spinel. So what's going on? So in 1964, Buddington and Lindsley proposed the oxy-X solution model, in which some of the iron 2+ is oxidized to iron 3+ to form magnetite, and the rest of the iron 2+ and titanium is used to form ilmenite. Now, in their model, oxygen in water was used as the oxidizing agent, but this is problematic, partly because oxygen is not a particularly strong oxidizing agent, and because crustal fluids, they have very low oxygen, somewhere in the range of 10 to the minus 21 atmospheres. And so it would require a significant amount of fluids to have passed through the rock to be able to oxidize all of the oval spinel to ilmenite. Now, consequently, this would also have generated a significant amount of alteration, which at least in the Eastern Gabbro, we don't see. And what we do see in the Eastern Gabbro are fluid inclusions in both pyroxene and apatite that contain carbon dioxide and methane. So we suggest rather than oxygen being the oxidizing agent, it's a carbon being the oxidizing agent, with carbon 4+ in CO2 being reduced to carbon 4- in methane. Now this has two benefits. One, in that carbon is can be a stronger oxidizing agent than oxygen, and the second thing is that it can generate this oxidizing power without generating alteration because there's no fluids involved. So if all of these different textural varieties of iron titanium oxide simply represent different degrees of oxidation of the same high temperature solid solution, then their chemistry should be similar, their major element chemistry. So here we have another ternary diagram looking at the bulk composition of iron, titanium, and magnesium plus aluminum for these different textural varieties of oxides. And what we can see is that indeed their major element contents are almost identical, at least they overlap, which agrees with the idea that they represent the same solid solution. So something else that's mentioned by the oxidation model, or this oxy-X solution model, is that the more oxidized varieties, so in this case trellis textured oxides, they should have a higher iron 3+ to iron 2+ ratio than the more reduced varieties, so the cloth in this case. Whereas the titanium content should not be affected because it's not being oxidized. So here we have the same diagram as before, looking at iron 2+, iron 3+, and titanium for the different textural varieties of oxides in the Eastern Gabbro. And the arrows here are just connecting different textural varieties of oxides within the same thin section. So what we can see is the trellis varieties here in red, they follow the model in that they have a higher iron 3+ to iron 2+ ratio, and they lie along the magnetite ilmenite tie line, whereas the cloth varieties lie along the magnetite obospinel solid solution. Now, something else that we can see is that during this oxidation process from cloth to trellis, the titanium content is not being affected, and we can see this because the arrows connecting the samples are horizontal. So all of these mineralogical and textural and compositional features agree with this oxy-X solution model that was presented back in the day, with the only change that rather than oxygen being the oxidizing agent, we're suggesting that carbon is the oxidizing agent. Now, the trace element content of these iron titanium oxides should also reflect the oxidation process as a result of the iron titanium oxides interacting with an oxidizing and metal bearing fluid. So here we have a number of vector diagrams that illustrate the change in concentration of trace elements from cloth to trellis textured oxides within the same thin section. And what we can see is that the multivalent elements such as molybdenum and tin, and the mobile elements such as copper, they exhibit a systematic increase in concentration from cloth to trellis varieties, whereas the single valent elements such as chromium and zinc, they don't show any kind of trend with oxidation. Now, if we focus first just on tin, for this example, we can explain the consistent increase in tin concentration by tin occurring in its oxidized 4+ valence state, which is much more compatible into magnetite than is its reduced 2+ valence state. And the fact that it is so compatible agrees with the idea that it was being transported by an oxidizing fluid. Now that we have demonstrated that this oxidation process, although it has an effect on the chemistry of oxides, this effect is not particularly strong. So we can now use iron titanium oxide chemistry as a way to understand the genetic evolution of the Eastern gabbro. So before we do that, though, we have to understand how trace elements behave during magmatic fractionation. So here we have a binary diagram showing the variation in incompatible elements in blue and compatible elements in red as a function of magmatic evolution, with 0 here indicating completely solidified rock and 1 being completely melt. Now, based on the Rayleigh fractionation model, elements that are most compatible into a mineral will occur in their highest concentrations in the first minerals to crystallize, and in the lowest concentrations in the final minerals to crystallize, whereas the opposite is true for incompatible elements. So they'll be concentrated in the final minerals to crystallize. Now, in terms of magmatic evolution, more primitive melts, a small degree of fractionation will yield a very large change in the concentration of compatible elements, whereas the opposite is true again for evolved melts, where the greatest degree of variation will occur in the incompatible elements. So we're now going to use these fundamental geochemical features as a way to understand or characterize the genetic relationships between the different rock types and mineralized zones in the Eastern gabbro. So here we have 2 binary diagrams looking at the concentrations of nickel, chromium, and niobium in oxides hosted in the layered series in brown and metabasalts in blue. Now, just as a refresher here, nickel and chromium behave compatibly into magnetite, whereas niobium behaves incompatibly. So looking first just at layered series and metabasalts, we can see that the oxides in the layered series have lower concentrations of compatible elements and higher concentrations of incompatible elements compared to the metabasalts. And also the layered series exhibit a large range in compatible element concentration, but essentially no variation in the concentration of incompatible elements. And for the metabasalts, we can see the opposite trends. Now, because these these variations in trace elements here can or suggest that these two rock series crystallize from compositionally distinct melts, with a layered series crystallizing from a more evolved melt than the metabasalts, and which experienced only a small degree of fractionation after emplacement. Now, because the metabasalts are comparatively more primitive than the layered series, then this large range in niobium concentration that we see cannot be the result of just fractionation of a single batch of magma, but rather suggests that these metabasalt samples actually represent crystallization from different metabasalt, from different melts with slightly different trace element contents. So this would have generated the different metabasalt units that we see within the Eastern Gabbro. Now, moving on to the marathon series, we can see that oxides here are compositionally intermediate to the metabasalts and the layered series, in that they have a very small variation in nickel content, but a very large variation in both chromium and niobium content. Now, because chromium and niobium behave geochemically different with respect to compatibility into iron titanium oxides, then these systematic variations cannot be explained simply by the fractionation of a single batch of magma, but suggest that this rock series actually crystallized from multiple batches of compositionally distinct melts. And this idea is consistent with the fact that the marathon deposit is a conduit type system, in which a characteristic feature is this multiple inputs of new melt. So looking now at the mineralized zones in the marathon deposit, here we're illustrating the variation in nickel and zirconium content in oxides in the footwall zone, main zone, and W horizon. Now we can see that for both elements, there is a systematic increase in concentration from the footwall zone up to the W horizon. Now, just as we explained before, because nickel and zirconium behave compatibly and incompatibly into iron titanium oxides, they should not exhibit the same trends if you're looking strictly at magmatic fractionation. But what we see here is that they behave geochemically similar. And so these variations cannot be explained again just by fractionation of a single batch of melt, and suggest that each of these zones actually crystallize from compositionally distinct batches of magma, again consistent with this idea of a conduit type system. So now that we know, now that we have used iron titanium oxides as a petrogenetic indicator, or a way to understand the petrogenesis of the Eastern Gabbro, we're now going to shift on to whether or not we can use their chemistry as a way to identify barren and mineralized rock. So over the past decade, there has been quite a bit of work looking at or characterizing the composition of oxides hosted in different mineral deposit types and in both mineralized and barren systems. But at least in terms of nickel copper PGE systems, this was largely done with regards to nickel-rich systems. But the Eastern Gabbro is different in that it is quite nickel poor. So it's important for us to know whether or not the relationships that were described in earlier studies are applicable to these compositionally different copper PGE systems. So here we have a number of box whisker diagrams looking at the composition of chalcophile elements in iron titanium oxides. And what we can see is that there's really no systematic change in the concentrations of these elements in both mineralized and barren rock, with some barren rock being enriched and some barren rock being depleted in chalcophile elements. So this indicates that the chalcophile element content of oxides is not a particularly robust indicator of mineralization, and implies that you really need to take into consideration a lot of other information when you're making these interpretations, such as the timing of crystallization of the oxides relative to the saturation of a sulfide liquid. So keeping on the topic now of mineralization, we're going to shift our attention to looking at the mineralogy and texture and chemistry of sulfides as a way to understand the processes that generated the different styles of mineralization throughout the Eastern Gabbro. So sulfides in the Eastern Gabbro are mineralogically quite variable and can exhibit both equilibrium and non-equilibrium textures. So in the footwall zone and main zone, sulfides consist predominantly of variable proportions of pyrrhotite and chalcopyrite, with the footwall zone having a higher pyrrhotite to chalcopyrite ratio. The W horizon is quite unique in that it contains chalcopyrite and a significant amount of bornite with very little pyrrhotite. And the occurrences north of Marathon, so the northern occurrences, they also contain a significant amount of chalcopyrite and pyrrhotite, but also a significant amount of cubonite that we don't see in the Marathon deposit. Now, all of these sulfides can exhibit sharp rounded boundaries with each other and with their neighboring silicates and oxides. And these equilibrium textures are typical of sulfides that crystallize from a sulfide liquid. Now we can also get a range of non-equilibrium textures. Here we have a reflected light image showing these numerous islands of pyrrhotite that share ragged boundaries with a matrix of chalcopyrite. Now, something that's not really illustrated in this image here is the fact that many of these islands of pyrrhotite are actually in optical continuity with each other, implying that at one point they actually represented fewer larger crystals of pyrrhotite. Now, given this textural relationship, we suggest that this texture actually represents the replacement of primary pyrrhotite by secondary chalcopyrite that precipitated from a hydrothermal fluid. Now, we can also get a range of sulfide hydrosilicate intergrowths. Here we have two different chalcopyrite actinolite intergrowths that we suggest represent different processes. So on the left here, we can see that the actinolite blades exhibit a preferred orientation that is controlled largely by the cleavage of the pyroxene that they have replaced. Now, I think the most important thing to take out of this image is that this preferred orientation of the actinolite blades is maintained in the chalcopyrite that they are intergrown with. Now, the image on the right we can see is quite a bit different. The actinolite blades actually exhibit a random orientation in their intergrown chalcopyrite. Now, because chalcopyrite does not have a cleavage, then if it has been replaced by actinolite, then the actinolite blade should not exhibit a preferred orientation. And that's exactly what we see with this image on the right. And so we suggest this texture actually represents the replacement of magmatic chalcopyrite by actinolite. Now, this is obviously not the case with the image on the left, given the preferred orientation of the actinolite blades. And so we suggest that this texture actually represents the precipitation of secondary chalcopyrite from a hydrothermal fluid along with actinolite. Now, these different, if the equilibrium sulfides crystallize from a sulfide liquid, then their compositions should reflect the partitioning of metals between iron-rich monosulfide solid solution, so pyrrhotite and pentlandite, and copper-rich intermediate solid solution, so chalcopyrite, cubonite, and bornite. So here we have three binary diagrams looking at the concentrations of zinc, palladium, arsenic, and cobalt in the different different sulfides throughout the Eastern Gabbro. And what we can see is that zinc and cobalt behave the way that they're expected to behave, with zinc being enriched in the iron-rich sulfides and cobalt being enriched in the and zinc being enriched in the copper-rich sulfides. Now, palladium and arsenic actually don't behave the way that they should. One might expect that they may be concentrated in the copper-rich phases, but what we actually see is that they occur in similar concentrations in both the iron-rich and copper-rich sulfides, apart from pentlandite. So we can explain this this similarity in concentrations of the PGE and metalloids between all of these sulfides by the exsolution of platinum group metals, which would have increased the concentrations of the PGE and the metalloids, but would not have affected the concentrations of the base metals such as zinc and cobalt. Here we have the same diagrams as before, except the data points now represent the compositions of the non-equilibrium chalcopyrite. If these non-equilibrium chalcopyrite precipitated from a hydrothermal fluid, then their metal contents do not necessarily reflect the partitioning of metals between MSS and ISS, because they did not crystallize directly from a sulfide liquid. But what we can actually see is that based on the overlap between data points and the chalcopyrite field, we can see that the non-equilibrium chalcopyrite is compositionally quite similar to the equilibrium chalcopyrite. Now, because we have demonstrated texturally that at least some of these non-equilibrium chalcopyrite had to have crystallized or had to have precipitated from a hydrothermal fluid, then this similarity in composition suggests that the secondary chalcopyrite formed by the dissolution of primary chalcopyrite, mobilization of these metals, and then reprecipitation as secondary chalcopyrite with a comparable chemistry. So because the PGE content of sulfides was modified by the exsolution of platinum group minerals, we can't really use PGE concentrations as a way to infer magmatic processes. And so we need a proxy for the PGE. And in this case, we're going to be using sulfur selenium ratios. So here we have a binary diagram with sulfur selenium ratios on the x-axis and copper palladium on the y-axis with the range of mantle values overlain. Now, different processes will yield different trends on this diagram as a result of different sulfide liquid silicate melt partition coefficients between the included elements. So just to go over a few of these processes, if we have a high R factor, so if the sulfide liquid interacts with a large volume of silicate melt, this will generate lower than mantle copper palladium and sulfur selenium ratios, whereas lower R factors will generate mantle-like copper palladium and higher than mantle sulfur selenium ratios. Removal of sulfide at depth will generate high copper palladium ratios as a result of the preferential removal of palladium from the silicate melt. If we contaminate the melt with sulfur-rich sedimentary rocks, this will generate higher than mantle sulfur selenium ratios. And then in the opposite end, if we have sulfur loss or if we contaminate with sulfur poor rocks such as igneous or metamorphic rocks, then this will generate lower than mantle sulfur selenium ratios. Looking now just at the Marathon deposit, if we focus on the footwall zone and main zone in green and red, we can see that they have mantle-like copper palladium, but sulfur selenium ratios that range to values that are significantly higher than the mantle values, which suggests that both of these zones experienced variable degrees of contamination by sedimentary rocks by sulfur-rich rocks, with the footwall zone experiencing a higher degree of contamination. Now, this is consistent with earlier work looking at sulfur 33 values, which identified systematically negative sulfur 33 values in both the main zone and footwall zone, and interpreted these negative values as a result of contamination by Archean sulfur at depth. Now, looking at the W horizon, we can see that it is quite geochemically distinct from both the footwall zone and main zone. It has copper palladium and sulfur selenium ratios that are lower than mantle values. Now, this can largely be explained as the sulfide liquid here having experienced a much higher R factor than the footwall zone and main zone. But the variations in R factor alone cannot really explain the large range in sulfur selenium values that we see, some of which are very much depleted relative to the range of mantle values. Now, if we remember back a few slides, the W horizon is really the only zone in the eastern gabbro that contains a significant amount of bornite. Now, bornite is not a particularly common assemblage. It's not a particularly common mineral in nickel copper PGE systems and can require some specific processes to have operated in order to generate. Now, one of those processes is sulfur loss. So if we remove sulfur from the sulfide liquid, then this will affect the sulfur selenium ratios and can explain why we have such a variation in sulfur selenium in the W horizon. Now, moving northwards, we can see that the northern occurrences are geochemically quite different from the Marathon deposit, and they exhibit a range of copper palladium from values lower to values higher than the mantle values, and they have sulfur selenium ratios that are systematically lower than the range of mantle values. Now, the low copper palladium ratios can be explained largely by the sulfide liquid experiencing moderate to high R factors similar to the main zone and W horizon. Now, it's tempting then to say that the high copper palladium ratios are the result of low R factors, but this can't really be the case, mainly because even at very low R factors of around 100, copper palladium values will still be within the range of mantle values. And so it is likely actually that zones experience variable degrees of sulfide removal at depth, which preferentially removed palladium from the silicate melt. So what about the low sulfur selenium values? Now, I mentioned earlier that there's really two main processes that can generate lower than mantle sulfur selenium, one of them being sulfur loss and the other being contamination by a sulfur poor rock. Now, we can largely exclude sulfur loss as having had an effect on the sulfur selenium ratios here, mainly because we don't see any textural or mineralogical evidence for sulfur loss like we do in the W horizon with the presence of bornite. And so it's more likely actually that these zones were contaminated by sulfur poor rocks such as igneous or metamorphic rocks. And just as a reminder, the Marathon deposit, so the footwall zone and main zone, they were contaminated by sulfur-rich sedimentary rocks. So this demonstrates the complexity that can occur in these mineralizing processes, even on a relatively small scale. Now that we understand more about how the mineralization formed, how can we actually find that mineralization? So we're now going to shift our attention to whether or not we can use vein mineral chemistry as a way to vector towards this buried mineralization. So for this study, we sampled veins down the length of several drill holes, and we summarized this information initially in these downhole variation diagrams looking at lithology, assay, and vein density. And the most immediate thing that we notice is this relationship between metal content and vein density, in which rocks with a lower vein density corresponded to zones of mineralization. So this was really encouraging because this already can act as a tool for exploration, because it provides you a first estimate of where mineralization may be located along the length of a drill core. Now you might be asking yourself, well, what's the point? Why not just look if the rock has sulfides or not? And the reason for this is that some of these mineralized zones, particularly the W horizon, are quite sulfide poor. And so the only way that you can really identify them is by looking at whole rock metal assays. So by having this relationship with vein density, it provides you a kind of first pass as to whether or not mineralization may be present before you even send out your rocks to get assayed. So the mineralogy and texture of these veins is quite complex and quite challenging to characterize optically, and this is compounded by the fact that the minerals are extremely fine-grained. And so a lot of the characterization that we focused on was on major element chemistry. So here we have a ternary diagram showing the iron, magnesium, and aluminum content of these vein minerals. And we can see actually that they represent complex mixtures of iron and magnesium chlorite, actinolite, serpentine, and saponite. So before we can use vein mineral chemistry as a way to vector towards mineralization, we have to understand what it is that is actually controlling the chemistry of the veins. Now, this control can be very local, based on the composition of the mineral that the vein cross-cuts, or it can be at a slightly larger scale, based on the composition of the host rock, or it can be based on the chemistry of the fluids from which they precipitated. Now, ideally, the vein mineral chemistry should be controlled by the composition of the fluid from which they precipitated, because it is this fluid that's going to be mobilizing metals out of the underlying mineralization. So let's focus first just on the most local control and looking at host mineral chemistry. So here we have a number of box whisker diagrams looking, illustrating the difference in concentration of titanium, vanadium, and chromium in veins that cut across pyroxene plagioclase pairs and oxide plagioclase pairs within the same thin section. And what we can see is that anytime the veins cut across pyroxene and oxide, they are systematically enriched in titanium, vanadium, and chromium, indicating that at least these three metals are not being sourced from the underlying mineralization, but rather they're being sourced very locally from the host mineral, and so are not applicable to exploration because they don't reflect metals originating from mineralization. Moving to a slightly larger scale, we're now going to look at the host rock control on vein mineral chemistry. So we have two sets of box whisker diagrams here. The top diagram is looking at the composition of vein minerals that are hosted in metabasalts and marathon series in blue and purple. And the bottom set of diagrams is looking at the host rock chemistry, again with metabasalts in blue and marathon series in purple. Now looking first just at the composition of veins, we can see that cobalt, nickel, and zinc exhibit a difference in concentration between those veins hosted in metabasalt and marathon series. And so if this difference is controlled by the composition of the host rock, then we should see this difference in concentration mimicked in the whole rock chemistry. But if we look at it, that's actually not the case, with some marathon series actually being enriched in these metals compared to metabasalts. Now, in terms of the composition of the host rocks, we can see that copper exhibits a significant difference between metabasalts and marathon series being enriched in the mineralized marathon series. Now, again, if there's any host rock control, this should be mimicked in the composition of the veins. But again, this is not the case. The concentration of copper in vein minerals hosted in both rocks is essentially the same. So this lack of correlation between vein mineral chemistry and host rock chemistry implies that host rock may not play a significant role in controlling vein mineral chemistry. Now that we have a better understanding of what is controlling vein mineral chemistry, we can now take this into consideration and use vein mineral chemistry to try to develop a tool to vector towards mineralization. So here we have three downhole variation diagrams looking at the cobalt, nickel, and zinc content of veins as a function of distance from mineralization. And we can see that there's a consistent increase in concentration of these metals with increasing distance from mineralization. Now, this seems to suggest that there may be some control of the presence of underlying mineralization on vein mineral chemistry, but there's a problem. And the problem is that if the metals were actually being sourced from the underlying mineralization, then one might expect that the concentration of metals be highest in the veins closest to mineralization, but we're actually seeing the opposite. So maybe there's something else controlling the concentration of these metals in the veins. Here we have a similar diagram, except now we're looking at the variation in metal content as a function of distance from the footwall contact. And we can see a very similar trend to what we saw before, with an increase in concentration with increase in distance from the footwall contact. So this relationship suggests to us actually that rather than the metals being sourced from the underlying mineralization, they're actually being sourced by the progressive interaction of the fluid with silicates and oxides such as pyroxene, olivine, and magnetite as the fluid migrates upwards through the rock package. So putting this all together, what this actually means is that, at least for the Eastern Gabbro, vein mineral chemistry is not a particularly useful indicator of mineralization. Now, what I think the more important thing to take out of this exercise is the need to have a firm understanding of what is controlling the composition of your exploration vectors or of your mineral chemistry. Otherwise, you're going to get some weird results and potentially make some poor exploration decisions. So Now that we have a better understanding of all the processes that generated and modified the Eastern gabbro and the mineralization, let's now put this all together and rebuild the Eastern gabbro. So the first phase to be in place into the Archean metavolcanics was the metabasalts, and they were in place as multiple pulses of melt with slightly different trace element contents, and this generated the different metabasalt units that we see throughout the system. The layered series was in place next near the top of the metabasalts, and it was in place as a single pulse of magma, which later underwent fractionation in a relatively closed system. Now, the marathon series was in place last, and it was in place near the base of the metabasalt, with the trochlite sill in brown being in place first, followed by the main body of the intrusion. Now, as a whole, the marathon series crystallized from multiple pulses of compositionally distinct melts, which mixed to variable degrees depending on where you were in the system. So in the main body of the Pluton here, the mixing occurred to a much greater degree than in the oxide-rich pods, which occur above the main body of the intrusion and acted, almost as relatively closed systems. Sulfides likely liquated in all of these pulses of melt, and we know this because not only because the sulfur 33 values imply that saturation occurred at depth, but also if we look at mineral chemistry such as oxides, the chalcophyll element contents are similar in both mineralized and barren rock, implying that a sulfide saturation event sequestered all of the chalcophyll elements from the iron titanium oxides. Now, eventually, all of these sulfides accumulated into the zones that we see now in the Marathon deposit. Now, in the footwall zone, these sulfides experienced relatively low R factors, which generated the high copper palladium ratios that we see. Whereas in the W horizon, the sulfide liquid experienced a much higher R factor, which generated the low copper palladium values. Now, the W horizon is unique in that it also experienced variable degrees of sulfur loss, which generated the variable amount of bornite that we see. Now, cyanite was in place after all of this, and it crosscuts all of the gabbroic rocks, but we didn't really talk about this in the presentation because it doesn't have a particularly important bearing on the formation of the Eastern gabbro and the mineralization. So just as a quick comparison to the Marathon deposit, if we look at the northwestern occurrences, these zones experienced variable amounts of sulfide loss, sulfide removal at depth, which modified the PGE contents. They were contaminated by sulfur poor, either igneous or metamorphic rocks, and they did not experience any loss of sulfur like we see in the W horizon. After the Eastern gabbro and the mineralization formed, the system as a whole had to have been fluxed by oxidizing CO2 and metal-bearing fluids. And these fluids oxidized the iron titanium oxides from the cloth texture to the trellis varieties that we see. And all of those intermediate varieties that we talked about represent essentially this oxidation process frozen in time. This fluid event also likely mobilized metals from the primary sulfides and forming the secondary sulfides that we see that can be intergrown with hydrous silicates. And the final stage of the, modification of the Eastern gabbro is the fluxing of multiple fluids throughout all of the gabbroic rocks. And this generated the mineralogically complex veinlet system that we see. And it also mobilized metals, but these metals were not necessarily mobilized from the underlying mineralization, but rather by interaction with the silicates and oxides as the fluid migrated upwards through the system. All right, so that's everything for me. Again, I just want to say thank you to the CIM for giving me this opportunity and everybody who came out to watch this presentation. And if anybody has any questions, I'd be more than happy to try to answer them. Thank you.
Thanks, Matt. So if anyone does have any questions for Matt, we can either do it with the hand raising thing in the participants or the reactions feature on your Zoom account, or you can just speak up and ask away.
Nobody? Am I getting off easy?
Looks like that. I'm surprised,
Apparently.
given the people on the meeting. I thought there might be a few questions for you.
It was so perfect, just no questions.
Oh, Wyatt's got a question. Go ahead, Wyatt.
Matt, great presentation. I just had one quick question for you, just from the beginning. The oxidation that's driven, and you're saying that that's driven by a CO2-rich fluid, right?
Yeah.
Do you find any like of the other indicators of that? I mean, I guess I'm not quite familiar with the entire process, but do you find any like graphite overprint that's in the deposit that would also indicate the action of that process?
No, the main indications that we have for is just in fluid inclusions, both like the presence of CO2 and methane. But other than that, we don't particularly have an indication of the presence of CO2. I mean, like if we're looking at more acidic fluids, then I mean there's sericite alteration and whatnot. But other than that, there's no graphite or anything like that. Although we did think about that, but no.
What about the source of the CO2-rich fluids?
We don't know, at least not yet. I mean, at the time that wasn't the focus, but it might be something important to look into if this is an important process in these systems. And I mean, CO2 and methane, they're not uncommon in these systems, nor is the presence of these trellis textured oxides. So the process has to be relatively common. So it may be worth diving into this more in the future.
Excellent. Thank you so much.
Thanks.
Are there any other questions? If not, Greg, did you want to say anything about upcoming meetings?
Thanks, Pete, and thank you, Matt, for that wonderful talk.
Thanks.
It's kind of the kickoff to the CIM being a bit more active. We have 2 more talks. Well, SESME has 2 more talks this week, I believe on the 14th and the 15th, or the 13th and the 15th.
Yeah, we have a talk on
Can't
Wednesday
remember.
and a talk on Thursday. So.
And we have our first CIM Distinguished Lecturer on Wednesday, April 21st at 1 p.m. We have Eb Shrekus at talking about the social license to operate in a virtual world. So hope to see you all there. And